ever wondered how your phone can pull up a contact in a split second? Or how a website logs you in almost instantly? Well, the secret sauce is often a brilliant data structure called a hash table. So let's dive in and see how this incredible digital filing cabinet makes our modern world run so fast.
To really get why hash tables are so genius, you first have to understand the problem they were built to solve. And this quote, it just nails it. Picture trying to find one book in a massive, totally disorganized library. You'd be stuck there, literally checking every single title, one by one. What a nightmare. You know, this whole slow, painful process isn't just a fun little thought experiment. It's a very real problem in computer science. And that brute force, one-by-one approach, it actually has a name. It's called a linear search. You start at the very beginning and just chug along, checking every single item until, hopefully, you find the one you're looking for. Sounds simple, right? But there's a huge catch. And this is the killer. The more data you have, the slower it gets. If your library doubles in size, your average search time doubles too. In today's world of big data, that kind of system is completely useless. It just doesn't scale. We need a much, much better way. So, how do we fix our slow library problem? What if, instead of searching aimlessly, you had a magic tool? Something that could instantly tell you exactly which shelf a book is on just from its title. Well, that magic tool is what we call a hash function. Think of it like this. It's a clever little algorithm that takes some piece of information, we call this a key, like a book title or a username, and it mathematically crunches it down into a number. And that number is our special address, our index. The process itself is actually pretty straightforward. You feed it a key, like the name John Smith, you run it through that hash function, and bam, it spits out a number, let's say 18. That number tells us exactly where to store John Smith's data, and more importantly, where to find it later instantly. And the entire system, the whole library, with all of its shelves, or buckets as they're often called, that's the hash table. At its heart, it's just an array, but it's a superpowered one. That hash function lets us jump directly to the right spot without any searching. But what happens when the magic tool isn't perfect? And this is where we hit the plot twist. This leads us to the central challenge of using hash tables. See, we're trying to map a nearly infinite number of possible keys, like all the names in the world, to a very fixed number of spots. And sometimes things are going to overlap. This is the million-dollar question. What on earth do you do when our hash function takes two totally different names, say Sammy Sirius and Khalid Anas, and gives both of them the exact same index number, like 14? That right there is called a collision. It's when two different keys end up fighting for the same parking spot. And you might be really surprised to find out just how often this actually happens. Here's the wild part. Collisions aren't some rare bug or a sign that your function is broken. No, they're an expected mathematical certainty. And the best way to wrap your head around this is with something called the birthday paradox. It poses a simple question. How many people do you need in a room to have a better than 50% chance that two of them share a birthday? The answer is just 23. That's right. It feels totally wrong, but with only 23 people, it's actually more likely than not that two of them share a birthday. This is a perfect illustration of our problem. When you're mapping items into a fixed set of slots, like 365 days of the year, these kinds of overlaps or collisions happen way faster than our gut tells us they should. Okay, so if we know for a fact that collisions are gonna happen, how in the world do we deal with them? Well, this is where computer scientists got really clever. Let's look at the two main strategies. So on one hand, you have something called separate chaining. The idea here is that each bucket isn't just one slot. It's actually a little list. So if two books hash to the same shelf, no big deal. You just add the second book to the list for that shelf. You just start a little pile. The other popular method is open addressing. This is more like, shoot, shelf 18 is full. All right, let me just check shelf 19. Ah, empty, perfect. You just find the next available spot and put it there. So it's basically a choice between stacking things up or finding a new spot. So we've seen how they work, we've seen the problems, and we've seen the solutions. But when you put it all together, why are hash tables such a big deal? Why do they matter so much? Well, it all boils down to one simple, beautiful thing: speed. Just raw, mind-bending speed. I mean, just look at this chart. The difference is staggering. Compared to other ways of storing data, the hash table is in a league of its own for things like finding, adding, and removing items.
Look at that column. It says the performance is O of 1. But what on earth does that O of 1 thing even mean? That O of 1 is a fancy way of saying constant time. And here's what's so incredible about that. It means the operation is pretty much instant. And, this is the important part, it stays instant whether you have 10 items in your table or 10 million items. It just doesn't slow down. It's an absolute game changer. And because they are so unbelievably fast, I guarantee you are using them dozens, maybe hundreds of times a day without even knowing it. That contact list on your phone? Hashtable. Dictionaries in a programming language like Python? Yep, hashtables. They're used for database indexing, for caching websites to make them load faster, and for looking up your user account on basically every service you use. They are the hidden engine behind so much of our digital life. So hashtables offer this unbelievable, tantalizing promise, near instant performance for the things we do most often with data. And that sounds almost too good to be true, right? Which of course leads to the big question. What are the trade-offs? What's the hidden price we pay for all of that amazing speed? Now that's a great question to think about.